Hi, this is the second video of Chapter 8, Sampling Distribution. We'll keep introducing the idea of sampling distribution, but we're going to use a particular applet called Statkey this time so that we can do sampling, multiple samplings at the same time. Remember that in the first video, we did a small sampling distribution exercise, which is, we are selecting 5 numbers out of 1 to 10 numbers. And for each sample of 5 numbers, we calculate X bar, sample mean, and then we do this process over and over again so that we can come up with various different values of X bar so that we can talk about the distribution of X bar. This time, not only we're doing 5 times of sampling, we want to do this process for example, thousands of times. And when we want to do many times, you really don't want to do this by hand. So we will be using particular applets here. There are several different ones available there, but we will be using something called Statkey. So now I'm going to share my window here. So here is a topic. Sampling distribution. Okay, so before we actually go to the Statkey website, we're just going to introduce the example first. We'll be looking at 2015 salaries of all 868 Major League Baseball players in $1 million. So this is our data set, and we're going to actually do some sampling exercise with this data set. So this Statkey is available on this website. So we're going to just copy and paste that thing on your web browser, and then you can actually get to that website. or if you don't even want to do that, in Google, just type Statkey, and the very first one will be the Statkey one. So you just click that one. And then you will have this initial windows looking like that. There are various different things that you can do. Right now, we'll be talking about sampling distribution of mean. So we're going to just click that one here. Okay, so this is the window that we'll be playing with a little bit. One of the interesting thing about this site, it actually has also, already have a whole bunch of built-in data set. And one of them is baseball player 2015 salary in millions. You see that? So if you click that, and it will give you some information about our data set, especially when you click the show data table here, you will see the name of the players and then corresponding salaries. And there are 868 information there, so you can scroll down and see a lot of names and player names and their salaries 2015. Also on the right hand side, you can see a summary of the population information. Here I want to point out that this is a population, which means there are actually exactly 868 people the players were playing in Major League Baseball in 2015. So this is actually all the information. We happen to have the population information. There is a mean, there is a standard deviation. And there's also a little histogram available for the population as well. For now, I'm going to actually go back to our slide. And the first question I want you to think about is, what's the shape of the population distribution? How can you describe this population distribution? Okay, so let's go back to the Statkey. The shape of the distribution of this population, is this symmetric? Not at all, right? The symmetric means you have a right-hand side and left-hand side is exactly same to the center or from the center. But this one, you can see that there are a lot of values that are relatively small. And then there are a few values that are really big. But there are probably a little bit of potential outlier. but it's not symmetric at all, but it's actually very right skewed. Okay, so you can kind of summarize what we just said here. The distribution of 2015 MLB players' salary is unimodal, which means it has one mode, one bump, highly skewed right, with some potential outliers at high values. Second question I want you to think about is, what are the population mean salary and population standard deviation salary? This information is also available on the right-hand side of Statkey. Here is the mean salary. So it's a little over 4 million. The standard deviation is a little over 5 million. Be a little bit more specific. Your mean salary is $4.215 million and standard deviation is $5.481 million. Notice that your standard deviation is actually way bigger than mean salary. They're probably implying that this data is really spread out. Okay, so now we look at some characteristics of the population. We will go ahead and think about some sampling. So here's our population of size of 868. We will be first thinking about selecting a sample of size 10. So first, we're just going to have one sample of size 10, and then we're going to calculate the mean of that sample. To do so, going back to Statkey, one of the things that you can see here is, here's the sample size, that when you're taking sample, what size that we want to take a sample of. The default is n is equal to 10, which is what we're doing it right now. So we don't need to change it right now, but later on we probably have to change it depending on what sample size we want to play with. Here, one of the options is called the generate one sample. So we're gonna generate one sample first. So you're gonna click that button. So what it does is, out of this 868 data point, it will randomly choose 10 values. So there is 1, 2, 3, 4, 5, 6, 7, 8, and then there are some overlaps there probably. So there are 10 points were there. Okay, so out of that 10 random sample, the mean is 7.237. Okay, there it is. And then your standard deviation is this value. But anyway, so the mean, once you have this sample, they also calculate the mean, 7.237, and then they're gonna actually point out, put the point over there for X bar. Okay, so my first mean was 7.237, so I will be writing 7.237. Okay, so now what I want you to do is pause this video for a second, and you do the same thing twice more. Okay, so you got another sample size of 10 and calculate the mean, and another sample size of 10 and then calculate another mean. Okay, so what you can do is click one button, and here's another sample, and this time my mean is 2.402. And then, as you can see, once you have 2.402, another sample right here. So that was our first sample X bar value, and another sample mean value here as well. Okay, so there are two values, and they also calculate the mean of those two values, which is mean of the means, sample means there as well. But anyway, my second mean was 2.402, so I will be writing 2.402 here. Another one, I'll do another sample, then another 10 sample, size of 10, one sample size of size 10, and then my mean was 5.773. And again, there's another point, a new point here, and then they calculate the mean of these three means, which is happen to be 5.138. So anyway, my third mean was 2.775, what was it? 5.773. So I'm gonna, okay. Your own sample, if you actually pass and calculate or find your mean values, your value is probably not the same as this value because it is actually your own random sample. But anyways, we got the idea of sampling here. Now, again, one of the benefits of using this Statkey applet is we can do this multiple times, thousands of times, right? So we're going to try to do that. We stick with our salary data, MLB player salary data, and n is equal to still 10, but this time we're going to get the sample thousands of times at once. Go back here. So I'm just going to reset here. And then instead of, obviously you can click this button 1,000 times, then you're going to have 1,000 samples, or you can click a button called generate 1,000 samples. So if you click that, it will take less than a minute to generate 1,000 samples, but the idea is exactly same. They get the sample and then calculate the sample mean and put one of the dots here, right? And they do another sample and then calculate the sample mean and put the dots there. And then they do this about thousands of times. So each of these points are a sample of size 10. So if you can go over here and there, you kind of, you get kind of a little dizzy, but anyway, each points are your X bar. But this is a X bar distribution, the distribution of X bar. And a couple more information. Just like before, it actually calculates the mean of this all 1,000 numbers there. So out of 1,000 samples, the mean is 4.248, and also calculate the standard deviation of this 1,000 values. And we also call that standard error. The standard deviation of X bar has a special name called standard error. That's 1.758. Okay, so remember that. Going back to our slide, there are questions. Describe the shape of the distribution of the 1,000 samples. So that one is unimodal. It's not really extremely right-skewed anymore. Slightly, still a little bit of slightly right-skewed, not quite exactly symmetric, but maybe a little bit right-skewed. That would be probably the description we would use. So the distribution is unimodal, slightly skewed right, with maybe some outliers at high values. Average of 1,000 means and standard deviation of 1,000 means. And those are the values that you can find. 4.248, 4.248, and 1.758. 1.758. Sound good? Okay, so we're going to do the same thing for the sample size is equal to 50. So everything is exactly the same. You're just changing your sample size to 50 this time. Okay, so remember that we didn't need to change the sample size last time because it is the same as the default number. But this time we are going to change this thing to 50 and click OK. Then do the exactly same thing, generate 1,000 samples. Here we are. And again, each of these values are the mean of your sample. And we'll see the shape of the distribution. We'll look at the mean of the means and then standard error of this means. Okay, so how would you describe the shape of this data set? Is it roughly symmetric? Maybe, right? Close to symmetric. And there's a mean value and there's a standard deviation value. So we can summarize the shape of the distribution as unimodal and close to symmetric. And then we also need the information of average of the means and the standard deviation of the means, which is 4.214, 4.214, and then 0.762. 0.762. Sound good? And now we're going to do one more time with sample size is equal to 1,000. The same thing, except we're going to change this number to 100. Generate 1,000 samples. And now we see the shape again. That's actually very close to symmetric, a little flat. I mean, it's wide spread out, but it's pretty close to symmetric. And the mean value is 4.248, and standard deviation is 0.536. So the distribution is unimodal and close to symmetric. And this value is 4.248, 4.248. And standard deviation is 0.536. Okay? Saying that, we're going to actually try to summarize all that information in one slide. The purpose of this slide is we're going to look at the mean of the mean values, standard deviation of the mean values, shape of the mean, and how it is similar or different as we alter our sample size. In particular, when sample size is getting larger, 10, 50, and 100, what's going to happen to for each measure? That's what we're going to do. So here, our mean value was 4.248, so I'm just going to copy and paste it here. And then our standard deviation value was 1.758 there. And the shape of the mean was slightly right skewed. Is that the description that we used? Slightly right skewed. And it's equal to 50. 4.124 mean. And your standard deviation was 0.762. Copy and pasting. And then the word that we used was close to symmetric. Close to symmetric. When n is equal to 100, 4.248 0.536, and again close to symmetric. Sound good? Okay, now let's look at this table for a second and see for each column, for first, mean of the means, what's happening when sample size is going from 10, 50, and 100. Do you see a lot of change happening here? Not necessarily, right? I mean, it alters a little bit because it is based on a random sample. So you're not going to actually have exactly the same number all the time. And in fact, it is a little weird case, odd case that you have exactly the same number here and same number here. That's not necessarily actually true. But the whole point is these are about the same number, right? In fact, if you go back, the information, mu information, it was 4.215 is our population mean. And this value is actually quite similar. It stays about the same as our population mean, no matter what sampling distribution, sample size that we are talking about. On the other hand, if you look at the standard deviation of the means, it is actually happening. It's actually decreasing. Do you see that? 1.7, 0.7, and 0.5. So it is actually changing dramatically. There's some pattern that we'll talk about the standard deviation of the means. And the shape, it was with the relatively small sample size equal to n, it was just slightly right skewed. And then when sample size is getting larger, the distribution of means were actually close to symmetric. So if you summarize this information in the mathematical form, when we have a random sample of size n drawn from the population with mean, mu, and standard deviation of sigma, the sampling distribution of sample mean x bar, the mean of x bar is always somewhere around the mu, which is the population mean, no matter what the sample size is. Even with a small sample size, the mean of x bar will be stay close to the mu. On the other hand, the standard deviation of x bar has this pattern, sigma, which is the population standard deviation, over square root of n. So what's happening is when sample size gets larger, this value gets smaller, which means your distribution of x bar is getting skinnier when sample size is getting larger, which means you're going to have a better chance to hit with x bar that close to the mu value. Okay, so when your sample is based on really big sample, the chances that you're gonna get the x bar close to mu is actually pretty high. So in other words, the larger the sample size n, the less the sample means vary. So they have a smaller variation. And also, when sample size gets bigger, the distribution of x bar will approximately follow normal distribution, which is a symmetric and the mounded shape. So if the population itself is normal, it actually doesn't matter what sample size you're talking about. The distribution of x bar will be always normal because your population is normal. But for the non-normal case, the shape of the distribution of the sample mean will follow approximately normal distribution as your sample size is large enough. So that's what actually central limit theorem is, which we'll be talking about in the next slide. So in a way, using these baseball examples, I kind of lead us to central limit theorem, which is actually has a 3 component. When sample size is large enough, 1, your distribution will approximately follows normal, and your mean of the x bar will be close to population mean mu, and your standard deviation with a large n again is actually getting smaller, sigma over square root of n, because and when n is larger, your sigma of x bar, your standard error of x bar will get smaller, which is actually essence of central limit theorem. And we're going to talk a little bit more and the examples of central limit theorem in the next slide.